All right. Good day, students. How has been your day? I trust you had a good night rest. So, the class begins today, and your subscription is for 2 weeks, as I stated earlier. So, we are going to be handling 3 topics today. We are going to be covering what 3 topics today within this 1 hour. So, the first topic, we are going to be looking at dimension. We are going to be, I'll be teaching you on dimension, how you can have the dimension analysis of derived quantities. So I'm starting with surface tension. I'm starting with surface tension. I'll also be giving you the dimension analysis for work and energy, work done and energy. I'll also be giving you the dimension for power. I'll also be giving you the dimension for pressure. I will also be giving you the dimension for momentum, how to solve for dimensional analysis. With these 4 examples or 5 examples which I will show to you, you can actually analyze the dimension analysis for any derived quantities. So I did this earlier in class, but I will explain it again for the benefit of those persons which didn't understand. And I'll be entertaining questions from you. In any aspect you don't understand in this class lecture, feel free to DM me, ask me question, and I'm going to I'm going to explain it also in my WhatsApp platform. Okay, so surface tension. So I've already explained surface tension as the force acting on the surface of a liquid, making it to act like an elastic material, making it to act like an elastic material. So now, what is surface tension measured? How is surface tension being measured? Surface tension is measured as force times force over length, force over length. Now force, we know force to be as anything that can initiate change. Let me say, if an object is at rest, let's say this object is at rest, anything that is going to initiate change, that will cause this object to move from point A to point B. Let's call this point A, this point B. Anything that will cause this object that will cause change, or that will resist constant motion, is force. So surface tension is measured as force over length. And you know that length is measured in meter. Length is measured in meter. And meter is a fundamental unit. So we are not breaking this length down into into another unit, because it's a fundamental quantity, and it has a fundamental unit. But force, unlike force is a derived quantity, and it has a derived unit. Force is measured by mass times acceleration. Mass times acceleration. Mass is a fundamental quantity. Mass is a fundamental quantity, and it has a fundamental unit, which is kilogram. Mass is measured in kilogram. Kilogram is written as kg. But we are not going into that right now. So mass is a fundamental quantity, and it has a fundamental unit. Unlike acceleration is a derived quantity, and it has a derived unit. So we are going to be breaking down acceleration. Acceleration is equal to change in velocity over time. Change in velocity over time. Now, time is measured in seconds. Time is a fundamental quantity, and it has a fundamental unit, which is second. As for velocity is a vector quantity. it's a derived what quantity, but you know under derived quantity we have what we have the what vector quantities and the what scalar quantities. I will organize a video which I'm going to send to you guys, giving you examples of vector quantities and examples of what scalar quantities. But for the essence of this video, let's concentrate on what we are doing. So velocity, which is a derived quantity, is equal to what? Displacement over time. Is equal to what? Displacement over time. Displacement also is a vector what quantity. They are analogous to what? Distance. Distance, just like speed. Velocity is analogous to speed. Speed is equal to what? Distance over time. They are scalar quantity. They have magnitude, but they are not telling you about the direction. But like velocity is telling you about the direction, which is equal to displacement over what? Time. Time, as we know, is measured in seconds, which is a what? Fundamental what? Unit. And displacement is measured in what? Meter, which is also a what? Fundamental what? Unit. Okay, why did I give you all this? I just want us to know this basis before we go into what? Dimensional what? Analysis proper. So we have to know this what? Basis, so that we can work with this. We can work with this what? Established fact. Remember I told you earlier, we have 3 fundamental units, which is what? M stands for mass, L here stands for length, then T stands for what? Time. Now, on the basis of this, we use the what? Capital letter of their first alphabet. So we'll be solving with this. So now, first of all, velocity. Velocity, as we are seeing here, is what? Displacement over what? Time. Displacement over what? Time. Displacement is measured in meter. Displacement is measured in what? Meter. Just like distance, measured in what? Meter. So it will be under what? It will be represented as L. M here represents mass, which is measured in kilograms. So whenever you see anything kilogram, anything that is measured in kilogram, to be represented as M. Whatever you see any unit that is measured in what? Meter. Any quantity that is measured in meter, it will be represented as what? L. Okay, guys. Velocity is measured at what? Displacement over time. As I said, displacement, which has what? The unit meter, will be represented as what? L. It will be represented as what? L. Then time, which is measured in seconds, will be represented as what? T. Now velocity is what? Displacement over time. Displacement is measured in what? The unit for displacement is meter. So it's meter, so it's represented here as L over, which is divided by time. Time is measured in seconds. Time is measured in what? Seconds. So it's represented as what? T. So we have L over T. So L over T will be equal to what? L T raised to the power minus 1. Whenever you see this power raised to the power minus, you should know that is what this is what? A denominator. You know that it has a division sign. It has a what? Division sign. But should in case I said L times T, that would be equal to LT, right? If I say L times T raised to the power 2, it will be equal to what? LT raised to the power 2. There, it will not have a what? It will not have a minus what? Sign. But if it is L divided by T squared, this will be what? LT raised to the power minus what? 2. Minus 2 because what? Minus 2 because it has a what? Negative what? It's a denominator. It's a division what? Sign. Alright, so let's go back to our work. So I hope you understand. Okay, I will entertain questions as I said, and I'm taking it brief by brief, step by step, for those who may not have done this before. So velocity now. Our dimension analysis for velocity will be equal to what? LT raised to the power minus 1. So we go to acceleration. I'm trying to progress step by step until we get to what surface tension, so that it will be understandable. Acceleration. Acceleration, as I've stated here, and acceleration is what velocity over time. We have gotten the dimension now analysis for velocity, right? So I just take this dimension and place here, which is Lt raised to the power minus 1 over what? T. Remember, acceleration equals to velocity over time. Time is measured in what? Seconds. So velocity, this is velocity, Lt minus 1, which is velocity, over time. So therefore, the dimension now will be what? Lt raised to the power minus 2. And I hope you know how we got raised to the power minus 2. Because Lt minus 1, this is simply L over what? T. Lt raised to the power minus 1 means L to minus 2. Divided by T. Divided by T will be what? Over 1 over T. So we have T appears here 2 times as what denominator, which will be equal to what? To be equal to what? L T times T to be L over T raised to the power what? 2, which is equal to what? L T raised to the power minus 2. L T raised to the power minus what? 2. Okay, so that is what I'm doing. Let me shift the camera. Lt raised to the power minus what? 2. Alright. So that is how I got this. That's how I got this. So now force. Force is measured as what? Mass times acceleration. And remember, the unit for mass is what? Kilogram. And kilogram here is represented as what? M. So that's why I have M here, which is M times mass times acceleration. So acceleration is Lt raised to the power minus 2. So this is M times Lt raised to the power minus 2, which is equal to M L2 raised to the power what? Minus what? 2. So that is it for that. So now the surface tension. Surface tension, which is equal to force over length. Force over what? Length. So now we have the dimension for force, which is MLT raised to the power minus 2. So it will be MLT raised to the power minus 2 all over length. So length, L here will cancel L. So we are left with MT raised to the power minus what? 2. LT raised to the power what? Minus 2. So we are going to be entering the next what? Topic. Okay, we'll be solving. Okay, we have done for surface tension, so we'll be solving another derived quantity, and we'll be doing it bit by bit. Another derived quantity. So the next derived quantity I have here is energy. Energy so work done. They have the same unit. Remember, energy, they say, is the ability to what? Energy is the ability or capacity to what? Do work. So it is work done, not work done. Work done. Okay. So now, energy is what? Measured as what? Force times distance. Energy is equal to what? Force times what? Distance. So from the previous example I gave, you can see that force, we measured force as what? The dimension for force, dimension analysis for force is what? M L T raised to the power minus what? 2. So this represents force times distance. Remember, distance is what? Measured in what? Meter. distance is the unit for distance is what? Meter. And meter, let me write my MLT here. MLT. This is kilogram, this is the unit, this is meter, and this is second. So meter is represented as what? L. So this will be first times this will be what? MLT times what? L. So MLT times what? L. So that means which would be equal to what? M what times what? L raised to the power what? 2. T raised to the power what? Minus what? 2. So therefore our dimension for this will be what? Equal to what? M L T raised to the power L raised to the power 2 T raised to the power what? Minus 2. Alright? So alright, the next derived quantity we are going to be looking at will be power. Power. And power is measured as what? Work. Work what? Over what? Time. Work over time. Okay, so from the previous example, we saw that the what? Dimensional analysis for work. Dimensional analysis for work is what? M L T raised to the power 2, L raised to the power 2, and T raised to the power minus what? 2. So this will be simple. That is work over what? Time. Time here, which is represented as what? T. So this also means M times what? L raised to the power 2 all over what? T raised to the power 2 times what? 1 over what? T. So now you can see we have what? T appearing what? 3 times. So this will be equal to what? M L raised to the power 2 and T raised to the power what? Minus what? 3. Because T square, which means T times T times this other T, so it will be what? T raised to the power minus what? Minus 3. Okay, that is that for what? Power. Alright, the next derived quantity we are going to be solving for the dimension analysis will be pressure. Pressure. And pressure is measured as what? Force. Force over what? Area. Force over area. And we know the unit for what? Measuring area is what? Meter what? Meter square. The link I sent to you, the first video I sent to you, the link, you will see where I gave some derived units and fundamental units, and I also give their what? Unit for what? Measurement. Derived quantities and their unit for what? Measurement. Then force, we are going straight to solving for the dimensional analysis. And the dimension analysis for force, as we saw earlier, is what? M L T raised to the power minus 2 all over area. Remember again our 3 fundamental what? Units. M L T. M, which is mass, is measured in kilogram. L is measured in what? Meter. Then T is measured in what? Seconds. So our area, which is M raised to the power minus 2, M raised to the power 2, which is M square, will be represented as L. L will be representing what? Any derived what? Any derived or fundamental quantities that is being measured in what? Meter. And area is measured in meter, so it will be represented as L. So this is the dimension for what? Force. So area now will be what? L raised to the power what? 2. Let me come again. Area, the unit for measuring area is what? Meter what? Square. Meter square. And I told you that L will represent any quantity. L will represent any quantity, either derived or fundamental, that is being measured in meters. So we are using L to represent this, so it will be what? L raised to power what? L raised to power what? 2. Now, this is the same thing as M times L times T raised to power what? Minus 2 all over L times L. L square means what? L times what? L. So 1 L here will cancel what? 1 L. So what do I have now? I have M T raised to power minus 2 all over what? L, which is equal to M L minus 1 and T raised to power minus 2. I told you, whenever you see a negative sign here, minus 1, you should know that it's coming from a what? Division. It's a denominator. It's what? A denominator. So it's represented as L raised to power minus 1. So this is the dimension what? This is the dimension analysis for what? Solving pressure. So we are going to be looking at one more. I'll be entertaining your question on my WhatsApp platform. So feel free to send in your questions. I'll be entertaining your questions. So we are going to be looking at one more quantity, and that will be momentum. Momentum, which is equal to mass times velocity. Momentum, which is equal to what? Mass times what? Velocity. Okay, our mass is measured in kilogram, right? Our mass is measured in what? Kilogram. MLT. So it's measured in kilogram. So momentum will be equal to what? M. Kilogram is represented as M here, times velocity. From our last example, we saw that velocity is equal to what? Velocity is what? L T raised to power what? Minus 1. LT raised to power minus 1. So we just multiply it. So this will give us M L T raised to power minus 1. So this is the dimension what? Analysis for what? Measuring what? Momentum. So the next topic, which I'll be liking us to take, is called state of matter. State of what? Matter. Now, basically, from our secondary school, we know that matter exists in what? 3 states. Matter exists in what? 3 states. Solid state, liquid, and what? Gas. But here, I'll be showing you another state that matter can exist. Matter can also exist in a state called plasma. Plasma. I remember, what is matter? Matter is defined as what? Anything that has what? Anything that has mass and can occupy space. Anything that has what? Mass and can occupy what? Space. And now in the universe, this plasma state of matter, say matter exists in this state about 99%. 99 what percent? Because all the stars in the galaxy, all the stars in the galaxy, including the sun, they exist in this state of matter, which is called what? Plasma. The plasma was state. And I'll be explaining this to you. But we are going to be looking at their conversion. We're going to be looking at their what? Conversion. Their conversion from one state to another. The conversion from one state to another. Now, gas can be converted to liquid. So this is gaseous state to liquid. Now, the process whereby gas is what? Converted to what? Liquid is called what? Whereby a gaseous state is converted to what? Liquid state. This is called what? Condensation. Condensation. And the process whereby a liquid is converted to what? Gas. It's called what? At its boiling point, it's called vaporization. Vaporization. This is the process whereby a liquid state of matter, a matter in liquid state is converted to what? Gaseous what state at its boiling point. At its what? Boiling what? Point. And we have different boiling points for different what? Liquids. But evaporation is different. Evaporation is a process whereby a liquid is converted from a state of matter is moved from liquid state to gaseous state with that below its boiling what point, below its what boiling point. For example, you see a liquid. Let me use an example, a simple illustration. Water on the road after a downpour. So that liquid does not really need to reach the boiling point of what water, which is what 100 degrees what Celsius, for it to what convert to gaseous state. So that process is called what? Evaporation. So you should know the difference between evaporation and what? Vaporization. And that will be an example question. Thank you. So let's look from gaseous state, from gas to what? Solid. So let me put it like this. From gas to what? From gas to what? Solid. And from solid to what? Gas. It's process whereby a solid, an object in a solid state, is transformed into a gas. It's called what? Sublimation. Sublimation. Normally, using water as an example, the solid is supposed to pass. The solid is supposed to what? Pass through what? The liquid state. Solid is supposed to what? Convert from the. Sometimes it's supposed to move from solid to liquid state before what? Going to what? Gas. But the process whereby this solid substance move directly towards a gaseous state of matter without passing through liquid state is called what? Sublimation. So the opposite, the process whereby gas move a substance move from gaseous state to solid state is called deposition. Deposition. All right. So this is also a possible exam question. So we are going to be looking at the next state. So we are going to be seeing from gas to plasma. From gas to plasma. From plasma to gas. The process whereby the substance move from gaseous state to plasma state is called ionization. It's called what? Ionization. Then from plasma state to gaseous state is called what? Recombination. Recombination. So because of time, I will not be giving you a detailed note yet on this, but I will do that later. Now, we're going to look from solid state, to liquid state, which is common. This other one is common. The process whereby an object moves from solid state to liquid state is called what? Melting. And water is a common example. Then from liquid to what? Solid state is called what? Freezing. Alright, so that is that for state of matter. I'll be entertaining your questions. So we are going to be looking at okay, students, before we move to osmosis and diffusion, you know I gave an assignment in osmosis and diffusion. I'll be explaining it in this class. I'll be explaining that assignment in this class. But before I move into that, I would like to explain this solid, liquid, gaseous state and the plasma state of matter. The plasma state is not something I can illustrate with a diagram, but probably with a slide, or like a projection, because it cannot be represented like this other words three. But for these three, I'll also be explaining the plasma state of what? Matter. Now, what is the solid state? The solid state of matter, in solid constituents, you can see that the particles which can be atoms, can be ions, or can be molecule, they are closely packed together. As you can see in the solid state, you can see that they are closely closely packed together. So the forces between the particles are so strong. They are so strong that the particles cannot move freely, but can only vibrate. So as a result, a solid has a stable definite shape, and it has a definite volume. A solid has a definite shape. It also has a definite volume. Unlike liquid, as we can see in the diagram, liquid can only take the volume of its container. Liquid does not have its own solid it does not have a definite shape. It takes the shape of its container. It also takes the volume of its container. You can also define a liquid as a nearly incompressible fluid. A liquid can be defined as a nearly incompressible fluid. It cannot be compressed. That it conforms to the shape of its container. So it retains nearly constant volume independent of the pressure. So the volume is definite if the temperature and pressure are constants. Okay, for the gaseous state of matter, a gas is a compressible fluid. A gas can be defined as a compressible fluid. Not only will a gas conform to the shape of its container, but a gas has a nature of expanding. It expands and it conforms to and fills the container. I will use an example: a gas cylinder. When you are filling your gas cylinder, when they are filling the cylinder, you can see that the gas takes the whole shape of the cylinder inside. You are not seeing it because it's not something that can be seen with physical eyes, but it expands. It's compressible. It's a fluid that is compressible, and it expands and it fills its container. Understand? Now we're going to also look at the plasma. I'm going to explain the plasma state of the plasma state of matter. A gas is usually converted to a plasma in one or two ways, either from a huge voltage difference between the 2 points, or by exposing it to an extremely high temperature. So you can take this down as note. You can write down, a gas is usually converted to a plasma in one or two ways, either from a huge voltage difference between 2 points, or by exposing it to extremely high temperature, causing electrons to leave the atoms, resulting in the presence of free electrons. Now, you can stop writing for now. Let me explain. In a plasma state of matter, the electrons are free. The electrons are free. Normally, for a molecule to be formed, they have to be. Let me use an example. In water, for instance, let me say water is H2O. H2O, right? So this is hydrogen ions combining with oxygen ion, right? They are coming together to form water. But in a plasma state of matter, all the ions are free. All the ions are free. So there's no combination. So you can continue with the note. I say this creates a so-called partially ionized plasma at very high temperatures, such as those present in stars. It is assumed that essentially all electrons are free, and that a very high energy plasma is essentially is essentially bare nuclei swimming in a sea of electrons. Example, I told you, example of substance in plasma state of matter is the sun. The sun, corona, some types of flames, the stars, all of them, all these are all examples of what? Illuminated matter. They are called illuminated what? Matter. Illuminated what? Matter. All their ions are what? Free. All their ions are what? Free. And as I said, the plasma is by far the most abundant of all four fundamental states of matter. It constitutes about 99% of all ordinary what? Matter in the universe. All right. So right now I'll be discussing osmosis and diffusion. So first of all, let's look at osmosis. I know you all have done this in secondary school, but I'll be giving an example, I'll be giving an illustration, and at the end of the day, we are going to look at how these things we are doing, how it relates to nursing practices, how all this relate to what nursing what practices. So what is osmosis? Osmosis, it is a spontaneous net movement. Osmosis is a what? Is a spontaneous net movement of solvents. Is a spontaneous net movement of solvent molecules through a selective permeable what? Membrane from a region of high water potential. Please listen to me attentively. Osmosis is a spontaneous net movement. I'll be giving an illustration on the board, but please listen attentively. Osmosis is the spontaneous. When they say something is spontaneous, it means something happens naturally on its own. It happens what? Naturally on its what? Own. So osmosis is what? Spontaneous net movement of solvents. Solvent, example of solvent, water. Solvent is anything that can what? Dissolve in a what? Anything that can what? Dissolve. Example, water. Anything that can dissolve a solute is called a what? Solvent. Water, for example, is called a universal solvent. Let's say this is water. So the water here is the solvent. Then the solute is what is dissolved. Like let's say sugar cube. Sugar cubes. These are called the solutes. These are the substances that dissolve in the what? Solvent. Then when the substance is dissolved, it's formed what we call a solution. So a solution will be equal to what? Solvent plus solute. Solvent plus what? Solute. So let me come again. I say osmosis is spontaneous net movement of solvent molecules through a selective permeable membrane from a region of high water potential, in bracket, a region of lower solute concentration, to a region of low water potential, that means a region of higher solute what? Concentration. Let me come again. I say it's a spontaneous net movement of solvent molecules through a selective permeable membrane from a region of what? High water potential, which is a region of lower solute concentration, to a region of low water potential, which is a region of high solute what? Concentration. So let me explain. Let me give a very simple illustration. Let's say these are two vessels, and let's say we have the volume of water here is up to this level, then the volume of water here is what? Up to this what? Level. So this is actually, these are two what? Different. Let's call this A and let's call this what? B. So from this definition, it's trying to tell us that solvents moving from a what? From a region of high water potential So this contains more water. So this solvent now, example water, is moving from what here, which they have what high what water potential, to here that has what lower what water what volume or what potential. Do you understand? Moving from what here a high water potential to what lower what water what potential. Now in brackets, as I explained, I wrote there region of low state, low solute concentration. Low solute concentration. What that means now is the solute. For example, now let's say the solute, let's use sugar for example. If I put a cube of sugar now in this water up to this level, and I put another cube of sugar, let me say another 1 cube of sugar, let's use an example, 1 cube of sugar. If I put 1 cube of sugar into this cup, and I put 1 cube of sugar into this other cup, this one has what high water what content, this other one has low water content. You will discover that the concentration of the sugar here will be lower than what here. The concentration of this sugar, if you taste it now, you see that the concentration of the sugar here that contains lower water content, lower water volume, will be what more. The concentration of this sugar here, if you taste this water, it will be more sugary than what this other one that contains what more water. So that is what it means. So let me read it again. I say it's a spontaneous net movement of solvent molecules through a selective permeable membrane from a region of high water potential, which is this high water potential, it has contain more volume of water, in brackets region of low solute concentration, to a region of low water potential, which is region of what high solute concentration. Okay, let me explain diffusion. Diffusion, what is diffusion? Diffusion is a phenomenon where molecule spread from region of high concentration area to region of what low concentration area. So they are not the same. Diffusion move what from high concentration. This diffusion move from high what high concentration to what low what concentration. So diffusion is movement of what is a move, especially the diffusion can involve both liquid or what gas. It moves from what a region of what high concentration to a region of what lower what concentration. And there are many transport systems in the body whereby our body receive food, our body cells receive food, our body cells receive energy, pass energy from one cell to the other, or to another cell. During the metabolic process, they undergo this process of what diffusion to move what energy in the form of ATP, adenosine triphosphate. And also diffusion also is involved in digestion of food, and I'll be explaining that in our next class. So I would like to be entertaining your questions. And if there's any example, any particular thing you didn't understand, I will explain it with a video. I will explain it in a video, and I will send it directly to the person. So in case you have a question, you pen down your question accurately down, you send it to me. I will make a short video to answer that question, then I will send it to you directly. So thank you very much. I'll be expecting your questions.